All right, so we were talking about, let's see, it would be nice if we got this far. We probably won't, but it would be nice. Okay, so we were doing gravitation. We were talking about page 379, number 8. So basically we had 3 masses. They were all 5 kilograms. And then we were trying to figure out what the net force was going to be on object B, which we said was going to be the vector sum of those forces coming from masses A and masses B. So we kind of drew in where those were, and we actually figured out what FA was. And FA is going to be in the positive y direction. So if I wanted to, I could even write that FA was 1.85 times 10 to the negative 8 newtons times J. And then we need to use our handy-dandy formula again and figure out what the magnitude of FC was going to be. And that's, again, G, M, B, MC all over RC squared. And then remember that G is that universal gravitational constant, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. It's the distance between B and C. That's what RC is. Just like RA was the distance between A and B. And then the masses are the same, so they're both 5 kilograms. And the distance between B and C is 0.4 meters. And that's squared. So our magnitude of FC is with newtons. All right, let's see if somebody else can confirm that. Get the same thing, Maddie? Okay. And that would be in the I direction. So that was going to be my next thing, is we would say that FC, the vector, would be 1.04 times 10 to the negative 8 newtons in the positive I direction. But what does the problem actually ask us to find? $379. So we need to find the magnitude and direction. And what we've really found here are the X and Y components of the net force. Okay, so we've got FA was 1.85 times 10 to the negative 8th newtons J, and FC was 1.04 times 10 to the negative 8 newtons I. And remember that our F net is the vector sum of all the forces that are acting on B. And so this is supposition principle, where we're taking the objects in pairs and figuring out what that gravitational pull is between those pairs. So because we've only got two forces and because they point in perpendicular directions, FC is going to give us F net X and FA is going to give us F net Y. So what's the magnitude of F net going to be? Yep, the square root of the sum of the squares of those components. How many sig figs do we have running around here? 3. Okay, 2.12. And then we can always kind of say that this is going to be our F net. This is F net X. This is F net Y. This is going to be theta, right? Because I think it told us to measure it with respect. Did it say with respect to the x-axis? Well, we're going to measure it. So tangent theta would be what from my triangle here? Okay, so F net Y over F net X. We know what those components are, so what's theta going to be? Good. Okay, so we all agree. So this is just a problem that's about applying the supposition principle and using that equation. Above plus x-axis. Okay. So figuring out the gravitational force or the gravitational acceleration anywhere above the Earth isn't too hard. We talked the other day about how we're just going to treat the Earth as a series of concentric spherical shells, and then we know that they're all going to be centered at the center of mass in the middle. But what do we do if we're talking about inside the Earth? So if we still assume that we can think of the Earth as concentric spherical shells, and again, we say that the mass is uniformly distributed, which again, we know it isn't, but that's beyond the scope of our class. Then we say that only the mass at radii interior to the radius we're talking about contributes to the gravitational force. So if this is going to be the Earth, and here's going to be the center of the Earth, and I'm talking about a little mass here that's at some r prime that's smaller than the radius of the Earth. then what physics ends up telling us is that it's only the mass that's inside that radius that contributes to what my gravitational force is going to be. So I'm calling the mass that's inside radius r prime me prime. And we'll talk about how to figure that out in a minute. But I would say that the gravitational force is going to be G, that mass that's internal, times whatever the mass of my particle is, times r prime squared. Or I'm sorry, divided by r prime squared. And then the question is, how do we figure out what ME is? Anybody have any ideas how we figure out what ME prime is? Yeah, if we know the density and we assume that it's uniform, and this kind of goes back to that linear density thing that we talked about when we were finding center of mass, when we were working with rotational inertia. If the density is uniform, then whether I take the whole Earth and divide it by its whole volume, or I take the part that's interior to r prime and divide it by the volume that's interior to r prime, those things have to be the same. If it's uniform density, no matter where I take the scoop, the ratio of the mass to the volume has to be the same. That's what uniform density means. So that means that I can find the mass of the Earth that's inside my radius as 4/3 pi r prime cubed times rho. And I just substitute that back into my formula. We got what we need? All right. So let's talk about that for a minute. So at the surface, that gravitational force would be G, the mass of the Earth, times the mass of my object, divided by r Earth squared. So as an object travels deeper into the Earth, what's going to happen to the force of gravity? Why do you think it's going to increase? So what variable up here is changing as you get, Maddie, as you get closer to the center of the Earth? Okay. Okay, so r is going to get smaller, so that would make f of g bigger, but me is also getting smaller because you're including less of the Earth. So you kind of have these competing effects as you go deeper, right? So inside, we said the formula was Fg, G, Me prime, little m, over, what did we call it? R prime squared. But what did we say Me was? Me prime was, excuse me. So Fg is really going to be proportional to R prime. So what's going to happen as you go deeper? First of all, what happens to R prime as you go deeper? It gets smaller. So what happens to the gravitational force as you go deeper? That, according to that equation. According to, yeah, the gravitational force. If R prime is getting smaller, what should happen to the gravitational force? It should get smaller too. Yeah. Right, because remember, we're talking about being inside the Earth. But the Earth, well, we're not yet. We're still going to die. That's not really the point. Plus, you've got to push out and hold the tunnel open the whole way down. If you go deeper than 12 feet, you got to brace the sides of the tunnel. So, you know, this is kind of ridiculous. But the Earth isn't actually uniform, right? So because the Earth is not uniform, as the particle goes deeper into the Earth, F gravity actually increases until a certain depth. And then decreases. As the particle continues to fall. So if you had drilled a tunnel, a mohole, I think they call it. And if you read science fiction books, sometimes they'll talk about grav tubes. And they use this, where you actually fall through the Earth and you come out on the other side. So you can go from London to Tokyo in like an hour and a half. And they evacuate the tunnel so there's no friction. There's no air resistance. And you free fall and you come out the other side and they use magnetic braking. But it's crazy. And science fiction. But, you know, science fiction and science inform each other. No. Because he was written back in the 50s. It happens. There's a reason why the first space shuttle was called Enterprise. And it never flew, which is ironic. And it annoyed a lot of people who were true trekkers. All right, so now let's go back and talk about U-graph, because that's going to change too, or at least we can talk about it again. So back in chapter 8, what was the formula for U-grav? MgH. So we can at least ask ourselves where that formula came from. And where did any and all of our potential energy formulas come from? We actually derived this formula using a relationship, and we did the same thing for the spring force. Okay, so change in potential energy was equal to negative work. I can go with that. And if I have a non-constant force, how do I write work? Yeah, of f of x dx. Or actually what I'm going to write it as here is f of r dr. Because all I'm talking about is the separation between two things. Okay, and really the equation that you should know, because when you get that pop quiz on equations that will eventually come, you know, in April, is that f is equal to negative du dr, which should look familiar from reading potential energy curves, or dx, du dx, if it makes you happy. But you should know that those are all pretty much dummy variables anyway, and I can put whatever variable I want and it doesn't change what I'm doing. Okay, so I can find UG now as the negative of the integral of fg of r dr. We'll talk about the limits in a minute. And I can make that the integral. What's my expression for fg now? Well, it can be between any two objects. It doesn't necessarily need to be between the Earth and an object, but I'm just going to make him capital M and lowercase m because it makes me happy. Okay. And I'm going to take this from some initial separation r until my objects are separated by infinity. Well, because when my objects are separated by infinity, what's the force between them going to be? Infinitesimally small, and so infinitesimally small that we will make it 0. So you can solve this integral. This is easy, right? I can pull out my negative GMM. I've just got my integral from r to infinity of dr over r squared, which, to make your lives easier, I'm actually going to write as r to the negative 2 dr. And you have come to an integral, my friends. And what's the first thing we ask ourselves when we come to an integral? Can we solve it by inspection? Can we solve that by inspection? Heck yeah. All right, so that gives me negative g big M little m. What do I get for my antiderivative? What? Divided by negative 1. From r to infinity. I probably should have had a dummy variable in there. I don't really care. I made these before I pretended to be a calc teacher. These are the 16th time I have used these notes. Okay, so my negative 1's cancel. I get GMM 1 over r. And actually, in fact, I'm going to write it this way. Over r from r to infinity, just for the moment. And then I'm going to substitute in. So I'm going to get GMM over infinity minus GMM over r. What's going to happen to this? that going to be equal to? 0, right? It's something over infinity. Not to mention it's something pretty small because g is times 10 to the negative 11. So honestly, even if you're talking about a planet, it's still going to be something really small. Okay? So what that tells me is that my gravitational potential energy is going to be negative g big M little m over the separation. Now, you gotta be careful because there's no r squared anymore. It's just r. Don't screw it up because you will. This also changes the point where gravitational potential energy is equal to 0 because this assumes that UG of infinity is equal to 0. Which actually makes sense. If those two particles are infinitely far apart, they're not going to be interacting with each other at all because they are infinitely far apart. And you also need to remind yourself that this is associated with a system of big M and little m. And that gravitational potential energy, which is actually what we said way back in the beginning with chapter 8, potential energy is a property of a system. It's a property of a configuration of particles. We kind of get lazy about it when one of those particles is the Earth and the other particle is the ball that I'm dropping or the elephant or whatever. But that is no longer true at all. It is purely a function of big M and little m. Okay? Well, it depends on the situation, which equation you use. If you're dropping something near the surface of the Earth or you're rolling something down a hill and you want to find the gravitational potential energy at the bottom, you're going to use MGH and you're going to tell me where U grav is equal to 0. If I tell you that there are 4 particles hanging out in the middle of space somewhere and I want you to find the gravitational potential energy of that system of 4 particles, you're going to use this. Okay? If it looks like a different situation than the one you've had, you're going to use this. If it looks like something falling on Earth, then you're going to use what we used in chapter 7 and 8. That's my next slide right here. If I have a multiple system, okay? So if we have more than just 2 particles, so multiple objects, so I'm going to say that I've got M1 and M2 and M3, and so these are separated by R12, and these are separated by R23, and these are separated by R13. And I want to find the potential energy of the system. I add them up in pairs. So my UG is going to be negative G M1 M2 over R12 minus G M1 M3 over R13 minus G M2 M3 over R23. And keep in mind that these are all negative and that gravitational potential energy in a system like this is always going to be less than 0. Okay, and that's a really important thing to remember. Because you can't have negative distance, you can't have negative mass, at least in Newtonian mechanics, which is where we live and where you're taking this class. we can't have negative mass, so the gravitational potential energy is always going to be negative when we're dealing with it in this kind of a situation. Okay. The next thing to ask yourself is, can we go backwards? Can we recoup our old formula? Of course we can. So our new formula for G, if we take the absolute value, is G big M little m over R. And if we pretend, for instance, that we're on the surface of the Earth, then big M can be M Earth, and little r can be the radius of the Earth. So I can rewrite this as G M Earth over R Earth times little m. But what's that? Staring at it might help. Looking back to your notes from yesterday would probably help too. Ah, so it's what? But it could be that, right? Yes. So, well, it doesn't matter. It's the same thing. I was trying to make a point by calling it AG. Okay, so that's going to be mg radius of the Earth. I happen to have said I was standing on the surface of the Earth and that's where my object was. If I brought my object up here, plus that, and if I reset my 0 point to the surface of the Earth, then that UG would be mgh, the height above the Earth. So I can recover what it was that I lost, or that I decided was too simplistic. Okay. So it's all consistent with itself. All right, we good? We got it? Okay, so if I have some object standing at the surface of the Earth, it's a little more squashed than usual. So I've got something on the surface of the Earth, and those two objects have a gravitational pull, right? And they have an amount of gravitational potential energy. So what if I want that little m to actually be able to leave the surface of the Earth? I'm going to have to give it a certain amount of what to, oh, what am I going to have to do? How is it going to be able to leave the surface of the Earth? It will need a force that will give it a what? They'll give it kinetic energy. And what's something that's very closely associated with kinetic energy? What's the formula for kinetic energy? And what's the V? Actually, it's not velocity. It's speed, remember. Okay, so I've got to get it up to a certain speed so that it has enough energy to pull away from that gravitational force that's creating a potential energy. And we call that speed. Anybody remember what we call that speed? Anybody did the reading? Call it escape speed. All right. So we want to talk about what that escape speed is. Oh, I was supposed to do the example problem first. Well, I guess we're doing escape speed right now. We'll go back and do the example. Okay. So when we're talking about escape speed, we're talking about a specific situation. So first of all, as the object rises off of the surface of the Earth and it's launched with a certain velocity, as that object rises up, what happens to the kinetic energy? As the object has that initial kinetic energy and moves up, what happens to the kinetic energy as it rises? It should what? Really? It'll decrease, right? When I throw the eraser up in the air and I give it a certain initial kinetic energy, what happens to it? The kinetic energy decreases, and what does that kinetic energy become? Potential energy. So the problem is that what happens to my eraser? It stops because all of its kinetic energy has become potential energy, and then that force pulls it back down. What happens if I give it a bigger kinetic energy? It goes farther. So what I have to do, and what this escape speed is the kinetic energy or the speed that I need to give it so that it doesn't get to that point where it stops. Now, the problem is that the potential energy never really goes away because that R value just keeps getting bigger and bigger and bigger. But we can play with conservation of energy, and we'll talk about that in a minute. So remember that UG is less than 0, right? And what does kinetic energy always have to be? Greater than 0. Okay. So our total energy, we will pick this up tomorrow because we have plenty of time tomorrow. At least